In this video we're going to talk about electronegativity, symbol chi. This is the ability of an atom in a molecule to attract electrons in bonds towards itself. This is a really useful concept for thinking about chemical bonding, but it's actually one that's difficult to put numbers to. There's been many attempts to do this using bond energies and ionization energies, for example, but any scale is not absolute. The most commonly used scale is that due to Pauling, and this has fluorine having a value of 4 and cesium having a value of 0.79. There are some general trends in how electronegativity changes across the periodic table. As we move across a row, the nuclear charge is increasing, and this pulls electrons closer to atoms, and so electronegativity increases across each period. But as we go down a group, the atoms get bigger and bigger and bigger, and the pull on the electrons decreases, and so electronegativity decreases down a group. Put these two things together, and as we go diagonally down, electronegativity is approximately constant. But there are some exceptions to these general trends. When we get down to row 4, we introduce the D block, the transition metals, and then later on the F block. So when we move across row 4, we're introducing a lot of extra elements. These extra elements means extra nuclear charge, and this results in higher electronegativity for the elements that follow than we might have predicted, and more complicated behaviour, particularly for groups 13 and 14. So for group 13, the general trend of decreasing electronegativity we see between boron and aluminium, but there's actually higher electronegativity for the next element, gallium, because of all that extra increase in effective nuclear charge that the transition metals have introduced. So let's have a look at what electronegativity can do for us. So a pure covalent bond has two atoms which are identical. The pull on the electrons in the bond is equal from the two atoms, and so we end up with a pure covalent bond with equal sharing of the electrons. But if the atoms are different, the electrons are pulled more towards the atom which is more electronegative. So in this HCl molecule, the electrons are pulled in the bond towards the chlorine which is more electronegative, and it ends up having a higher number of electrons and a partial negative charge. Whereas the hydrogen, which is less electronegative, loses control of the electrons in the bond and ends up with a partial positive charge. Now we can estimate these charges. In a pure covalent bond, each atom contributes one electron, and the two electrons in the bond are equally shared. So there's no charge on either atom. They start off with one electron, and they end up with half share of the pair, and so the partial charge is 0. But in a polar covalent bond, those two electrons in the bond, the fraction that are on each atom depends on the electronegativities of the two atoms. So we can define the partial charge as being 1 minus the pair of electrons shared out between those atoms. We do this using the electronegativity of the atom divided by the sum of the electronegativities of the two atoms. So for hydrogen, we have the electronegativity of hydrogen divided by the sum of hydrogen and Cl, and for chlorine we have the electronegativity of chlorine divided by the sum of the electronegativities of hydrogen and chlorine, and this shares out the electrons and gives us an idea of the partial charges. So let's put some values in using Pauling electronegativities of hydrogen at 2.2 and chlorine at 3.16. We calculate the partial charge on hydrogen, 1 minus 2 times 2.2 divided by 2.2 plus 3.16, and we work out a partial charge of plus 0.18. The least electronegative element ends up with a positive charge, whereas for chlorine the calculation is the same, except we now use the chlorine electronegativity on the top, and we work out that the partial charge on chlorine is the exact opposite, minus 0.18. So here's our polar bond with about charges of plus and minus 0.2 on the two ends of the bond. An estimate is all we can do. But if the electronegativities of the two atoms are very different, the electrons in the bond could be pulled completely onto the more electronegative element. So the electrons in the sodium-chlorine bond end up completely on the chlorine, which means our partial charges will become full negative charges or full positive charges. We have a full negative charge of -1 on the chlorine and a positive charge of +1 on the sodium, and we've ended up with an ionic bond. So what will we have? Will we have a pure covalent bond, a polar covalent bond, or an ionic bond? How can we predict? as we've just seen, as the electronegativity difference increases, there's a continuous change from covalent to polar to ionic. And we can use the difference in electronegativities as a guide. If the difference in electronegativity is 0, or quite small, perhaps lower than 0.4, we can consider the bond to be a pure covalent bond. If the difference is medium, if it's between 0.4 and say 2, the bond is considered a polar covalent bond. And if the difference is large, say larger than 2, the bonding is essentially ionic. So in a chlorine molecule, where the electronegatives at the two ends are the same, the difference is 0 and we have a pure covalent bond. In a HCl molecule, the difference is 0.96, so we have a polar covalent bond with partial charges. And in sodium chloride, we have a difference of over 2, 2.23, and so we have an essentially ionic bond. This is only a prediction and only gives us a gauge, but it's a nice handle on the type of bonding that we might have.